Unit 3, Interpolation and Approximation. Interpolation and Approximation. Okay, first let us see about interpolation. Interpolation. What is the concept of interpolation? Let us see. Here, that means here we discuss the problem of approximating. Here we discuss the problem of approximating a given function by polynomials. What is the meaning of this? One function is given, for example e to the power of x function is given. I have to express e to the power of x as polynomial, or approximate e power x as polynomial, or sin x is there, sin x, I have to approximate sin x in terms of polynomials. That is the concept of interpolation. There are two main reasons. There are two main uses of these approximate polynomials. The first one is to reconstruct the function f of x. Reconstruct the function f of x when it is not given. Explicitly. What is meant by explicitly? What is the meaning of explicitly? Means f of x equal to sin x, or f of x equal to cos x, f of x equal to e power minus x. That function will not be given for you. Only f of x is given, just a function f of x. It is not sin x, not cos x. F of x is given as directly f of x. I don't know what is that function. So f of x is not given explicitly, means just f of x will be mentioned for you as a function. That's it. Okay, it is not given sin x, cos x, or like that. Okay, that is the meaning of not given explicitly. Given explicitly means yes, f of x equal to something, sin x or cos x or e power x, like that. Not given explicitly means f of x is given just as f of x. Okay, when f of x is not given explicitly, and only values of f of x and are it's a certain order derivatives. It's a certain order derivatives are given. At a set of distinct points. At a set of distinct points called nodes or tabular points. Okay, this is the first use. That means what here? That is, what is the meaning of this? The x versus f of x will be given. X values, some x naught, x1, and so on, xn. Corresponding f values will be given, f1, f2, fn. Okay, then find f of x. Approximately satisfies the data. That means f of x is not given explicitly, but f of x values are given f0, f1, f2 at certain points called tabular points. That is x0, x1, xn are called nodes or tabular points. And the second use is to perform the required operations. To perform the required operations which were intended for f of x, means like determination of roots, differentiation and integration. Determination of roots, differentiation and integration. To perform required operations which were intended for f of x. That is what is the meaning of the x versus f of x will be given for you. That is data will be given x1, x2, xn. Okay. And f0, f1 and so on, fn. This data will be given for you. Then find what is f dash of something, f dash of some x1 or f double dash of some x3, like that, or integral of x0 to some xn f of x dx, like this. What is this value, what is this value, what is this value? Okay, this is one more useful of interpolation. Okay, and can be carried out using the approximate polynomial p of x. Okay, now the point is, one more point, the approximate polynomial p of x, the approximate polynomial p of x can be used to predict the value of f of x, at a non-tabular point. What is the meaning of this? The data is given, x versus f of x will be given, tabular points are x1, x2, xn, and the function values at these tabular points f0, f1, fn. Okay, then f value at f of x at some non-tabular point. You take for example non-tabular, outside the point, at xn plus 1 or at x equal to x minus 1. Okay, one can find. Then f of x, this is nothing but we are finding approximate polynomial for f of x approximated by p of x, and its value is at x equal to at non-tabular point. These are the not table point. It is the not a table point. To understand clearly, for example, if I consider one data 0, 1, 2, something 10, 11, some 20, then find f of x at x equal to 1.5. It is not tabular point. Tabular point means 0, 1, 2. These are the tabular points. 1.5 is not tabular point. Then for this one also we can use interpolation. Okay, now the deviation or difference, the deviation of p of x from f of x, the difference of p of x from f of x, that is, one can write deviation or difference means f of x minus p of x. F of x is exact function, p of x is approximative function, therefore is called error of approximation, So finally, using interpolation, what we are finding, an approximate polynomial only. And using interpolation we can find only the polynomial, not any other function. Remember this point. Okay, next one is, let f of x be a continuous function defined on some interval closed a comma b and b prescribed at n plus 1 tabular points x0, x1 and so on xn such that a value is equal to x0 less than x1 less than x2 less than and so on less than xn endpoint, and endpoint is equal to a equal to x0 and b equal to xn. What is the meaning here? I am assuming the function f of x as continuous function over the interval a b, and f of x values are given at n plus 1 tabular points. See, x0 to xn, how many points? 0 to n means n plus 1 data points, nothing but tabular points. F of x is prescribed at these n plus 1 data points, means f of x is known at x0, at x1, at x2 and at xn. Now the distinct tabular points x0, x1, xn maybe these tabular points may be non-equispaced means not equally spaced, meaning the difference between x0 and x1 is not equal to difference between x1 and x2. Non-equispaced, I am giving here clearly, x1 minus x0 not equal to x2 minus x1 not equal to and so on, like this, non-equispaced. Okay, or maybe equispaced. Equispaced means what? That is equispaced, that is x1 minus x0, x2 minus x1, x3 minus x2, all these are equal to some constant, fixed constant. So one can write, I can write this is xk plus 1 minus xk equal to h, xk plus 1 minus xk equal to h, k equal to 0, 1, 2 and so on up to what? Since n data points are there, xn is the last point, so k equal to n minus 1. Okay, this is data, equispaced data or non-equispaced data. For equispaced data, what is the condition? Xk plus 1 minus xk equal to h. Now the problem of polynomial approximation. The problem of polynomial approximation is to find a polynomial Pnx. The problem of polynomial approximation is what? To find a polynomial Pnx. Why Pnx? Because it is nth degree polynomial of degree less than or equal to n, which fits the given data. What is the data? Xi versus the function fi. Okay, which fits the given data exactly. That is, what is that? Pn, the polynomial at every data point must be equal to f of xi. I is from 0 to n. This, then the polynomial Pnx is called. Then the polynomial Pnx is called interpolating polynomial. Okay, the conditions take this as 1, the conditions given in equation 1 are called interpolating conditions, okay. Now how can I justify through n plus 1 distinct points nth degree less than or equal to nth degree polynomial is obtained? Let us see one remark. What is that? Through two distinct points, one can construct a unique polynomial of degree 1, right? Of degree 1. That means 2 points are there. I can construct a straight line, degree 1. Nothing but what is this is? Straight line. Okay, next. Through two distinct points, we can construct a unique polynomial. Of degree 2, nothing but parabola, or a unique polynomial of degree 1, nothing but straight line, okay. That is, okay, means what? If there are 3 polynomials like this, I can construct one parabola, or if the points are like this, I can construct a straight line. This is the choice. Therefore, that is, through 3 distinct points, we can construct a unique polynomial. Of degree. What is the degree? Either it may be 2 or 1. So of degree less than or equal to 2. Therefore, now the main point is, this is important. What is that? In general, through n plus 1 distinct points, we construct a unique polynomial of degree what? Less than or equal to n. Okay, the interpolation polynomial fitting a given data is unique, and remember this point also. The interpolation polynomial, that means what is that? Pi of x. The interpolation polynomial fitting a given data, is unique. That means whatever we are finding the polynomial p of x, this is unique. Now finally, let us see what is the definition of interpolating polynomial. A polynomial p of x A polynomial p of x is called an interpolating polynomial. An interpolating polynomial if the values of p of x and oblique r, it's a certain order derivatives, it's a certain order derivatives it's a certain order derivatives coincide with those of f of x and oblique r. It's the same order derivatives, it's the same order derivatives at 1 or more tabular points, at 1 or more tabular points. Sorry. So what is the interpolating polynomial? Interpolating polynomial p of x satisfies or coincides the points of f of x, or the derivatives of p of x coincides with the same order derivatives at the tabular points. Now in more generally, so if there are n plus 1 distinct points a less than or equal to x naught, a less than or equal to x naught, less than x1, less than x2, less than and so on, less than xn, less than or equal to b. Actually this is equal to a equal to x naught and xn equal to b. X naught to xn, n plus 1 data points are there. Then the problem of interpolation is to obtain what? An approximate polynomial, right? Is to obtain an approximate polynomial p of x satisfying the conditions satisfying the conditions. What is the first condition? The first condition is p of xi, that means approximate polynomial at xi equal to f of xi, the function value f of xi for I equal to 0, 1, 2 and so on n. R, what I told you, R and oblique R, it's a certain order derivatives, right? So coming to second condition, what is that? P of xi equal to f of xi, this is function approximation. And one more is what? P dash of xi equal to f dash of xi, I equal to 0, 1, 2 and so on n. This is the derivative condition. Okay, more this is theoretical definition and this is mathematical definition. What is that? Either p is equal to f or p is equal to f as well as its derivatives also equal. Maybe first derivative, I have mentioned only first derivative here, maybe second derivative, maybe third derivative and so on. Okay, and take this as condition 1 and these two conditions as 2, equation 2. Okay, the next is the derivative conditions. In 2, the derivative conditions into may be replaced by maybe replaced by more general derivative conditions. More general derivative conditions. That means what? Not only first order, maybe second order, third order, and so on, involving higher order derivatives. More general derivative conditions involving what? Involving higher order derivatives. Higher order derivatives. And the conditions in one give rise to Lagrange or Newton, Lagrange and Newton interpolating polynomial. Lagrange and Newton interpolating polynomial. And the conditions into give rise to Hermite interpolating polynomial. What is the meaning of this? If I use the conditions to only function values p of xi equal to f of xi, then we can derive Lagrange's and Newton's interpolating polynomial. And the second condition, what is that? If p of xi equal to f of xi, and first derivative also same, p dash of xi equal to f dash of xi, then we can derive Hermite interpolation polynomial. And one more point I am telling, p of xi equal to f of xi, p dash of xi equal to f dash of xi, and let me consider one more double derivative, p double dash of xi equal to f double dash of xi, then we derive cubic interpolating polynomial. Okay, just this is the information. Now let us see Lagrange's and Newton's interpolations and their existence conditions. Now let us see Lagrange and Newton interpolations. Lagrange and Newton interpolations. Okay, first thing, first point is existence of interpolating polynomial. Of Lagrange and Newton's model. Existence of interpolating polynomial. What is that? First one, here let the given interval be closed a comma b, and a function f of x is continuous on closed AB. On this interval, the function f of x is continuous, meaning at every point the function value is defined. That is the meaning of continuity. Okay, and assume that here we assume that we have n plus 1 distinct points. We have n plus 1 distinct points, a equal to x naught less than x1 less than x2 less than and so on xn equal to b. The tabular points, okay, being of AB and the values of a function f of x, and that the values of f of x are known at these points, at these points, means tabular values are known at these points. What is that meaning? That is xi versus fi data is known for I equal to, what is from what point, 0 1 2 up to n, I equal to 0 to n. Okay, just for your idea, x versus f I am taking here x naught corresponding value f naught, x1 corresponding value f1, and so on, xn corresponding value fn. This table will be given for you. Okay, the data values is given. Then we have to find the polynomial. We have to find the polynomial. What is the type of polynomial? P of x equal to, what is the length of the data? N plus 1 data points are there, therefore nth degree polynomial. So I am taking a naught plus a1x plus a2x square, a general nth degree polynomial I am considering, an x power n, equation 1. I have to find this approximate polynomial P of x for what? Where P of x is approximated to what? F of x. P of x is approximated to f of x, which satisfies the condition. Since it is interpolating polynomial, satisfies the condition, which satisfies the conditions. What the conditions? Interpolating conditions, as I told you, Newton's or Lagrange's. P of xi is equal to what? F of xi, I equal to from 0 1 2 up to n. Okay, substituting these conditions, what conditions? These conditions, substituting the conditions, take this as 2. Okay, that is P of xi equal to f of xi. We obtain the system of equations, substituting the conditions 2 in 1, we obtain the system of equations. What are the equations? First one, if I substitute not P of x naught equal to f of x naught in the first equation, what I am getting? A naught plus a1 x naught plus a2 x naught square and so on, plus an x naught power n equal to, what is the function? F of x naught, P of x naught. Okay, I am giving here, what is that? In examination no need to write. P of x naught equal to f of x naught gives, next one, P of x1 equal to f of x1 gives, what is this condition? Second one, a naught plus a1 x1, a2 x1 square and so on, an x1 power n equal to f of x1 and so on, and lastly P of xn equal to f of xn, right? This gives what? A naught plus a1 xn, a2 xn square and so on, an xn power n equal to f of xn, right? Okay, now the main point is here, this system of equations, has a unique solution, or the polynomial P of x exists, if the Wandermans Wandermans determinant. Okay, this determinant is by eliminating the unknown parameters from this system of equations. What is the determinant? See, is v of x naught x1 up to xn is equal to this. From the first equation, write the quotients of the unknown variables a0, a1 up to an. In first equation, a0 quotient is 1, x0 is a1 quotient, and next one a2 quotient is x0 square, and so on x0 power n. In second equation, the quotients are x1 square and so on x1 power n. And lastly what, 1 xn square and so on xn power n. This determinant, to get unique solution means this determinant must be not equal to 0, your matrix theory. Okay, now I'm including one more variable in the von Neumann's determinant, xn minus 1, x0 to xn minus 1 only, and in place of xn I am considering x. Then what is this determinant becomes 1 x0 square x0 power n, 1 x1 square x1 power n, and so on. What is n minus 1 through 1 xn minus 1 n minus 1 square and so on n minus 1 power n, and lastly x, that means 1 x square and so on x power n. This is von Neumann's one more expression. Okay, just I'm giving the expression. Then by the properties of determinant, by the properties of determinant we get, that means let us expand the above determinant. What is the determinant? x0 x1 up to xn minus 1 comma x. If I expand this determinant, I am getting the value as x minus x0, x minus x1, x minus x2, and so on. This multiplication, last term is x minus xn minus 1 into a, where a is a constant. How to find this a? Comparing the coefficients of x power n on both sides. We get, comparing the coefficients of x power n on both sides, we get the value of a as a equal to 1 x0 square x0 power n minus 1, not n minus 1, 1 x1 square x1 power n minus 1, and lastly 1 xn minus 1 xn minus 1 square and so on xn minus 1 power n minus 1. Okay, and one can write using von Neumann's notation. I can write this as v of what, x0 x1 up to what, last row is up to n minus 1, Okay, therefore what I'm getting, let me write one more step. Therefore what is this, v of x0 x1 and so on xn minus 1 x value, that means this expression. Okay, this value can be now written as x minus x0 x minus x1 and so on x minus xn minus 1 multiplied by what is v value, von Neumann's determinant, x0 x1 up to what, xn minus 1. Okay, now in this expression substitute x equal to xn, this x equal to xn. Now substitute x equal to xn, then what we are having, v of x0 x1 and so on xn minus 1 and xn is equal to what I am getting. First let me write this von Neumann's determinant on the right side, up to what, this is n minus 1. Okay, and the product x minus x naught, what is that, becomes xn minus x naught, xn minus x1, and so on, xn minus xn minus 1. Okay, so this can be written as v of x naught x1 up to xn minus 1. This product, this entire product notation, one can write pi, right? Pi stands for product, I equal to 0 to how, where n minus 1, xn minus xi, xn minus xi. Okay, now applying this one recursively, applying recursively, we get, what is this, one romance becomes, this is our original one romance determinant, up to xn is equal to what, pi of I comma j equal to 0 to n, where I greater than j. Okay, xi minus xj, which is not equal to, what is Wonderman determinant, not equal to 0. Okay, actually one can stop at the Wonderman's determinants, big determinant not equal to 0 only. Therefore existence of Lagrange or Newton interpolating polynomial is this Wonderman's determinant x1 x2 up to xn must be not equal to 0. That's it. This is existence condition for the interpolating polynomial. Okay, and remember xi xj are distinct, xi and xj are distinct.